Quasi-hereditary algebras, lecture 14, RIngel dualities. Let us start with the setup and with recalling what we did on the last lecture. Let K be an algebraically closed field and A a finite-dimensional K algebra. Let L1, L2 and so on up to Lk be a complete and irredundant list of simple A modules, and since we wrote it in some order, this means that we have fixed a linear order on these simple modules. And we assume that our algebra A is quasi-hereditary for this order. In particular, for each I we have the corresponding standard module delta I, which is the quotient of the indecomposable projective Pi by the trace in Pi of all projectives Pj, where j is strictly greater than I. And we also have the costandard module nabla I, which is the intersection inside the indecomposable injective module II of the kernels of all homomorphisms from II to all ij's, where j is strictly greater than I. Then we have the category F delta. That's a full subcategory of the category of all finite-dimensional A modules, which consists of all modules which have a filtration with standard subquotients, the so-called standard filtration. And we have also the corresponding category F nabla, which is the category of modules which have a filtration with costandard subquotients. We can look at the intersection of F delta and F nabla, and we call objects in this intersection tilting A modules. And in the third part of the course, we have discussed the following theorem by RIngel, which classifies indecomposable tilting modules. For each index I between 1 and k, there is a unique indecomposable tilting A module Ti with the following property. The module delta I is a submodule of Ti, and the quotient of Ti by delta I has a standard filtration. We have that the multiplicity of delta j in a standard filtration of Ti is positive only if j is less than or equal to I, and the multiplicity of delta I in Ti is 1. And any indecomposable tilting A module is isomorphic to Ti for some I. Then we have the characteristic tilting module T for A, which is the direct sum of all these Ti's, where I ranges between 1 and k. And finally, on the last lecture, we proved the following theorem. So we considered the algebra R of A, which is the opposite of the endomorphism algebra of the characteristic tilting A module T. We call this algebra R of A the RIngel dual of the algebra A. And we have proved the following theorem, which is also due to RIngel. Claim 1. The algebra R of A is a quasi-hereditary algebra with respect to the opposite of our original order on the index set 1 to k. Furthermore, the second RIngel dual of A is Morita equivalent to A, and the functor of taking a homomorphism from the characteristic tilting module to blank, that's a functor from A mod to R of A mod. This functor induces an equivalence between the category of all modules with a costandard filtration over A and all modules with a standard filtration over R of A. The inverse of this equivalence is given by the functor g, which is defined as tensor inverse t over R of A. And the functor f is usually called the RIngel duality functor. In this lecture, we start by recalling some properties of tilting modules, which we already mentioned before. So the characteristic tilting module T has the following properties. First of all, it has finite projective dimension. This is because A, being quasi-hereditary, has finite global dimension, so any finite-dimensional A module has finite projective dimension. Furthermore, the module T is self-orthogonal. This means that all extensions of positive degree from T to T vanish. This is due to the fact that T belongs to the intersection of F nabla and F delta, and we know that all extensions of positive degree from any module in F delta to any module in F nabla vanish. Okay, and finally we have the following property. There is an exact sequence which starts on the left with the algebra A considered as a left module over itself, so that is a projective generator of our algebra A, and then we can embed the algebra A in some tilting module, we can embed the cokernel in some tilting module, and after finitely many steps we end up with 0. In other words, the projective generator for A mod has a finite co-resolution by tilting modules. And this holds because we have seen that the module T is relatively injective with respect to the category F delta. And hence any object in F delta, in particular the module A, which belongs to F delta because our algebra is quasi-hereditary, so any object in F delta has a finite co-resolution by tilting modules. In the classical tilting theory for finite-dimensional algebras, modules which have these three properties are usually called generalized tilting modules. So this is a slight confusion with terminology. And for all generalized tilting modules, we have the following standard property, which we formulate here in our setup for our characteristic tilting module T. Theorem, that's the main result for today's lecture. The right derived of taking homomorphisms from T to blank. So the functor of taking homomorphisms from T to blank, it's a functor from A mod to R of A mod. So the right derived of this left exact functor is then a functor from the bounded derived category of A mod to the bounded derived category of R of A mod. So both A and R of A are quasi-hereditary, so they have finite global dimensions, so this right-derived functor is indeed a functor from dBA to dBr of A. And the claim of the theorem is that this functor is an equivalence. So let's prove it. So first of all, already on the previous lecture, we saw that this functor is full and faithful due to a lemma in Happel's book on derived categories. So what we need to prove is that this functor is dense. It is easy to see that an equivalent condition for this functor being dense is the property that any object in dBA is isomorphic to a complex of tilting modules as an object of this derived category. So we are talking about isomorphism in the derived category. Since the left regular A module has a tilting co-resolution, so it's isomorphic to its tilting co-resolution, so we have that the left regular module is isomorphic to some complex of tilting modules. By the additivity of this construction, we can get that any projective A module is isomorphic to a complex of tilting modules. Now if we take any object in dBA, we can represent it as a complex of projective modules. So any object of dBA is isomorphic to a finite complex of projective modules. And now we can take the standard iterative construction, we can co-resolve each projective component of this complex of projective modules by tilting modules, and then we use the self-orthogonality of T to glue these tilting co-resolutions of each component of our complex of projective modules into a complex of tilting modules. And this implies our main result. Let us now look at some example. Consider the path algebra A of the following quiver. We already looked at it in the previous lecture. So we have three vertices 1, 2 and 3, an arrow from 1 to 2 and an arrow from 3 to 2. This algebra is hereditary because there are no relations, and hence it's also quasi-hereditary. And it has 6 indecomposable modules. That's an algebra of finite representation type. The simple module L1, which is concentrated at the vertex 1, and since 1 is a minimal index, This simple module is also delta 1, nabla 1 and T1. And since there are no arrows which go into 1, L1 is isomorphic to I1. Then we have the simple module L2, which is projective because 2 is a sinc. So L2 is isomorphic to 2, and then hence it's also isomorphic to delta 2. We have the simple module L3 concentrated at the vertex 3. This source, so L3 is isomorphic to I3 and hence also to nabla 3. Then we have the indecomposable projective P1, which is concentrated at the vertices 1 and 2 with the identity map between them. This is isomorphic to nabla 2 and also to T2. We have the projective module P3, which is concentrated at the vertices 2 and 3 with the identity map between them, and this is isomorphic to delta 3. And finally, we have the indecomposable module I2, which is concentrated at all vertices with the identity maps representing the arrows, and this is isomorphic to T3. Okay, so now let us show that any module is isomorphic in the derived category to a complex of tilting modules. The module L1 is T1, so this module is already tilting, there is nothing to prove. The module P1 is T2. Again, this module is tilting, there is nothing to prove. And the module I2 is T3. That's a tilting module, there is nothing to prove. The module L2, which is a simple module at the vertex 2, which coincides with P2 and delta 2, that's a submodule of T2. L2, that's a module which is concentrated here, that's a submodule of T2, and the quotient is exactly T1. So the module L2 is a submodule of T2, and the cokernel of this embedding is T1. So L2 is isomorphic to the complex of tilting module where T2 projects onto T1. The module P3, which is delta 3, that's a submodule of T3, and the cokernel is T1. Let's look. This is P3, that's T3, we can embed P3 into T3, and the cokernel is exactly T1. So P3 is a submodule of T3, and the cokernel is T1, so P3 is isomorphic to the complex of tilting modules, where T projects onto T1. And finally, the module L3 is a quotient of T3, and the kernel this projection is isomorphic to T2. Let's take a look. That's T3, it has a quotient L3, and the kernel is exactly T2. So the simple module L3 is isomorphic to the complex of tilting modules given by embedding T2 into T3. And L3 is isomorphic to nabla 3, that's why we have this tilting resolution of T3. So we have checked that all modules can be represented by complexes of tilting modules in the derived category. Now let us discuss another type of RIngel duality. So the first RIngel duality functor which we considered was the functor of taking homomorphisms from a tilting module to blank. Of course, we can also take homomorphisms from blank to a tilting module, and this will give us a new functor we denoted by f tilde. So since T is a right RA module, this will be a functor from A mod to mod RA, from left A modules to right R of A modules. And of course, right R of A modules are the same as left R of A op modules. So we have the following proposition, that the functor f tilde from A mod to mod R of A, which is the same as R of A op mod, induces a contravariant equivalence between the category of all A modules with standard filtration to the category of all R of A op modules with a standard filtration. We can of course make this contravariant functor covariant by postcomposing it with the usual duality over the field. This will give us a covariant functor, the duality after f tilde, and this will be a functor from A mod to R of A mod. And then the reformulation of this proposition will look as follows. So this composition of duality after f tilde, and that's a functor from A mod to R of A mod, induces an equivalence between the category of A modules with standard filtration and the category of R of A modules with co-standard filtration. This equivalence maps tilting A modules to injective R of A modules and projective A modules to tilting R of A modules. And similarly, as we have just proved for the first kind of RIngel duality, the composition of the duality after the right derived of f tilde induces an equivalence from the bounded derived category of A modules to the bounded derived category of R of A modules. And all proofs for the functor f tilde are very similar to the proofs for the functor f. So we leave it to the audience. Let us do another example, which is a little bit more complicated. Consider the algebra beam given by the following quiver with relations. We have two vertices S and E, and two arrows, alpha from S to E and beta from E to S. And the unique relation is that alpha after beta is equal to 0. It is not very difficult to check that this algebra has finite representation type with 5 indecomposable modules. We have the simple modules Ls and Le, so Ls is the simple at the vertex S, and Le is the simple at the vertex E. We have the projective modules Ps and Pe. Ps is the indecomposable projective cover of Ls, and Pe is the indecomposable projective cover of Le. And we have the indecomposable injective envelope IE of Le. The indecomposable injective module Is is actually isomorphic to Ps. So here are the B modules written using their Loewe filtration. So these are the modules Ps, which is the same as Is, and Le. They all are uniserial, and here are their Loewe filtration. So for Ps, we can start at the vertex S, we have Ls on top. We follow alpha and go to the vertex E, then we follow beta and go back to the vertex S, and then we hit the relation. So Ps has lengths 3. Pe has lengths 2. We start at E, we have Le at the top, we follow beta, we come to S, we have Ls at the bottom, and then we immediately hit the relation. Similarly, IE has lengths 2. So we start at the bottom with Le, we can arrive to Le using alpha from Ls, and then we hit the relation. So IE has lengths 2 with stop Ls and socle Le. Next we claim that the algebra B is quasi-hereditary with respect to the order where S is smaller than E. Since S is the minimal vertex, then delta S is equal to nabla S is equal to Ts and is equal to Ls. And since E is a maximal vertex, delta E is equal to Pe, and we saw Pe here. Note that the multiplicity of Le in Pe is 1. And similarly, we have nabla E is equal to Ie. And the tilting module Te is equal to Ps and is equal to Is, sets this module. So it's projective, so it has a delta flag, it's also injective, so it has a nabla flag. Okay, and here we can see the standard filtrations of projective modules. So Pe is standard by definition, and Ps has Pe, which is delta E as a submodule, and the quotient is delta S. Okay, now let us look at tilting complexes which represent indecomposable modules for this algebra. The simple module Ls is tilting, so that's immediately clear. And also we have the tilting module Te, which is Ps and which is Is. The projective Ps is also obviously represented by a tilting module. Next, the module delta E embeds into Te and the cokernel is Ts. That's exactly this picture. Delta E embeds into Te and the cokernel is Ts. So delta E is represented by the complex of tilting modules, which is given by projecting Te onto Ts. Similarly, nabla E is a quotient of Te, and the kernel of this map is Ts. So nabla E, which is IE, is represented by the complex of tilting modules given by embedding Ts into Te. Finally, we have the complex which is given by embedding Ts into Te and then projecting Te onto Ts. So if we put Te in position 0, this complex looks as follows. So Ts, which is Ls, embeds into Te, into the socle, and then we project the top of Te, which is Ls, onto Ls, which is Ts. So in this complex we have homology at position 0, which is Le. So this complex of tilting modules is isomorphic in the derived category to the simple module Le at position 0. So that's the most complicated situation. Now we have a complex of tilting modules where homology is somewhere in the middle, not in the beginning and not at the end. Okay, let's explore this example further. So we have the projection pi from Te to Ts, injection iota from Ts to Te. The composition of pi after iota is 0. This means that the RIngel dual, which is the endomorphism algebra of T plus Ts, is actually isomorphic to the algebra B by sending iota to alpha and pi to beta. So we had the relation in B that alpha after beta is 0. Here we have homomorphisms pi and iota. The relation is that pi after iota is 0, but recall that R of B is the opposite of the endomorphism algebra, so we have to swap the guys in this relation. So it follows that the RIngel dual of our algebra B is actually isomorphic to B. There is a different way to look at this. We know that Te is equal to Ps and that Ts embeds into Pe. So given any endomorphism of Ps plus Pe, we can restrict it to Te plus Ts. And it's easy to see that this restriction induces an isomorphism between the endomorphism algebra of the projective generator for B and the endomorphism algebra of T. To sum up, the RIngel dual of B is isomorphic to B. Also, the algebra B has a simple preserving duality. It is isomorphic to B op by swapping alpha and beta, and so this algebra is isomorphic to its opposite algebra, which means that the category of B modules has a duality, and since our isomorphism preserves the idempotence, the duality is simple preserving. Okay, let's go further. Let us consider the complex of B modules given by the homomorphism from IE to PE, which is given by sending the top of IE, which is LS, to the socle of PE, which is also LS. So I is in F nabla, so we can resolve it by tilting modules. P is in F delta, we can co-resolve it by tilting modules. And then we can glue these resolution and co-resolution using this map to get the following complex of tilting modules. So we have Ts embeds into Te, then in Te we have the map iota after pi, which maps the top of Te to the socle of Te, and it also goes to Te. And then we have the projection of Te onto its top, which is Ts actually. So we have Ts, Te, Te, Ts, with embedding the map iota after pi and then projection. Obviously, if we go twice, we'll get 0. So this is a complex of tilting modules, and this complex of tilting modules gives us a tilting representative, so it's isomorphic in the derived category to this original complex given by mapping the top of IE to PE. And note that these complexes are, of course, isomorphic in the derived category. They are not isomorphic in the category of complexes for obvious reasons. We have more components in the second complex which are non-zero than in the first complex. Okay, we can also look at the complex given by taking the top of PE and sending it to the socle of IE. There is also a homomorphism between PE and IE in the opposite direction. But just like in the previous case, we can resolve IE by tilting modules, we can co-resolve PE by tilting modules, and glue these two resolutions and co-resolutions into a complex which represent the original complex P goes to IE. This will be complex now of length 2 because I is now in the right position and it has the resolution of length 2 by tilting modules. P is in the left position, it has a co-resolution of length 2. So we get a complex where the first component is T plus Ts, the second component is Ts plus Te, and the map between them is given by the following matrix. So Te goes by pi into Ts and by the identity to Te. Ts goes by 0 to Ts and by iota to Te. So in particular, we have here that the map from the T component here to the T component here is the identity map, which means that the corresponding trivial complex will simply split off as a direct summon, so we can kill it in the homotopy category. And again, we see that the two complexes are only isomorphic in the derived category and not in the category of complexes. Some extra problems and questions at the end. Problem question 1. Prove with all details that the right derived functor of taking Holmes from T to blank is an equivalence. Problem question 2. Prove with all details all statements about the contravariant version of the RIngel duality. Problem question 3. Prove that the algebra from the last example has exactly 5 indecomposable modules. Problem question 4. Prove that f delta in the last example is equivalent to its opposite category. Problem question 5. Prove with all details that B mod in the last example has a simple preserving duality. Thank you very much and see you next time.